I think we can start.
Shall I begin?
So Calum is going to talk to us about causal flow preserving optimization of quantum circuits in the ZX calculus. Take it away, Calum.
Perfect. So yeah, I'm Calum, and this is essentially my master's research at Oxford, and looking at causal flow preserving optimization of quantum circuits in the ZX calculus. So our general strategy is to take a quantum circuit, and this is not an original strategy, and then translate it into a ZX diagram, then simplify that ZX diagram in using the ZX calculus rules, and then extract that ZX diagram, a simplified ZX diagram, back into a quantum circuit. That's sort of the general strategy, and we're mainly looking to optimize the number of gates, the total number of gates, and in particular T gate count, the number of non-Clifford gates, and what this new strategy focuses on more is optimizing the number of two-qubit gates, so reducing that as much as possible. So initially we take our circuit and we can translate it into a quantum circuit, into the ZX calculus, and then now it's beneficial for us to translate this diagram into a graph-like ZX diagram. So what that means is we can convert all spiders into green spiders using Hadamard gates and the color changing rule. We can then fuse all together any Hadamard pairs, fuse together any spiders which can fuse together along non-Hadamard edges. Here, a blue Hadamard edge represents the Hadamard edge, so there's a Hadamard gate along that edge. And then we can add in identity spiders in order so that every single spider is a green spider, every single edge is a Hadamard edge, and the only spiders are connected to a singular input or output. And what this means is that we can then represent this as what is called the underlying open graph of the diagram, and then we can utilize this to look at graph-theoretic applications on this diagram, which becomes useful in looking at flow and how to optimize this. So once we have a diagram in a graph-like form, so all edges are Hadamard edges and all spiders are green spiders, Z spiders, we can then apply several rules. The first rule which we apply is ordinarily applied in previous optimization strategies, which is just the identity removal followed by Hadamard cancellation, and then immediately followed by spider fusion. But here I define it separately as a rule on its own, which maintains the graph-like structure of the form as it's convenient to for later applications. This is normally just applied iteratively throughout sort of the reduction strategies in ZX calculus and physics and things. But here I define it as a separate rule on its own. We also have local complementation, so this rule has been proven to hold in the ZX calculus, and it involves removing a spider of ±π/2 phase, and then complementing the edges of all the neighbors of that spider, and then updating the phases as shown. So it allows us to remove spiders with ±π/2 phase. And then the final rule, which were the main rules that we look at and which I use here is pivoting, which allows you to remove two spiders with integer multiple of pi phases, and then you complement the neighbors that complement the edges between the three different sets of neighbors of the set of neighbors which is only connected to one of the spiders, the set of neighbors only connected to the other spider, and the set of neighbors which is connected to both spiders. And then as parallel edges cancel, any edges that were in the same in local complementation, any edges that were initially connected together will cancel together. So these are sort of the three simplification rules which we use to reduce the diagram down. And often this is used to simplify the diagram down into a much more compact form. but not necessarily beneficial for extracting a circuit or reducing the number of two-qubit gates in the equivalent diagram. We also look at another rule, which is called neighbour unfusion. This has been introduced before in certain specific examples, but here we generalize it such that you can unfuse any subset of neighbours, and then it allows you to choose the phase of the vertex which you've unfused. It's essentially applying the identity fusion rule in reverse. So pulling a spider out, and it means you can choose the phase and the set of neighbours on any diagram. So for instance, if you wanted to apply pivoting in an example like this, and on a general phase, which may not be an integer multiple pi over 2, where you can ordinarily not apply pivoting, applying this neighbour unfusion will then allow you to apply pivoting on the two marked vertices here. So it allows additional applications. The previous cases of this, which have been applied, are on if there's a boundary vertex, then unfusing that onto a boundary vertex is done in the sort of full simplification routine, which is in physics, and also in a paper or a QPL paper last year by Staudacher et al. It was introduced formally as called neighbour unfusion, but they only specify to the case where you can only unfuse one neighbour. And then, but generalizing this to allowing multiple neighbour unfusions is actually incredibly beneficial for two-qubit gate reduction, as I'll show in a second. Another specific example of this is when you unfuse with no neighbours, and then this is essentially unfusing into what we call a phase gadget. So a phase gadget is a green spider with an arbitrary phase connected to a spider with zero phase by a single Hadamard edge. And this is done throughout simplifications. Once you have phase gadgets, you can apply, there are a few rules that you can apply. If the base spider picks up a phase of pi, then you can use the copy rule to pull that into a negative multiplier phase on the gadget. And there's also, you can use identity fusion to, if it only has one edge, then you can fuse it back into the graph. And gadget fusion allows you to fuse any two gadgets together which are connected to the same set of vertices. With phase gadgets, the full reduce algorithm of physics applies identity fusion, local complementation, pivoting, and it pulls out all non-Clifford phases, all non-Clifford spiders into phase gadgets. And then using this as every single one of these rules removes a vertex. So local complementation removes all interior vertices with plus or minus pi over 2 phase, and pivoting removes all interior vertices with integer multiple pi over 2 phase. You end up with a graph which is in reduced gadget form, meaning that every spider is either connected to a boundary spider, so connected to an input or an output, or is part of a phase gadget as a non-Clifford phase gadget. And you can always reduce this to this form, such a form where there are no interior Clifford spiders, and every single spider is non-Clifford. And this is the standard full reduced form. Now, once you've simplified a circuit, you need to then extract it back out or simplify the diagram. You need to extract it back out into a circuit, and all these transformations which are done within the full reduce algorithm have been shown to guarantee to preserve the existence of a graph-like property called G-flow. This arises from measurement-based quantum computing, and where it's required for a deterministic graph state. And whilst circuit extraction from general ZX diagrams has been shown to be P-hard, but there exists a polynomial time algorithm to extract circuits from diagrams with G-flow. So this means that when you reduce the diagram down using the previous rules into reduced gadget form, you can then extract a circuit. The issue is is that it's not necessarily optimal. It's very, very efficient for circuits with a low T count, so a low like proportion of T gates in the circuit. So for purely Clifford circuits, it's very, very efficient at doing this. But as the proportion of T counts increase, it can often produce a diagram by the extraction which has more two-qubit gates than the initial circuit had initially, as the diagram with G-flow doesn't have a direct circuit analog as such. In another sort of application of this, instead of extracting the circuit, once we have a circuit in reduced gadget form, we can apply a technique which was introduced called phase teleportation. So phase teleportation essentially allows you to take you essentially label all your non-Clifford phases with labels, and then you track them as they go through the circuit. So as they become gadgets, say for instance, we take these two general phases, alpha 1 and alpha 2, which at some point in the circuit, at some point they can become extracted into a phase gadget, and then if they become connected and maybe they pick up a plus or minus sign, which we denote this as M as phase multiplier, which is just plus or minus 1. And then this allows you to then they can fuse together, but then you can backtrack and do the exact same procedure as you did before, but unfusing the phases with different phases. And ordinarily, this is done where you set all other phases to 0 and set one phase to the sort of total sum of the phases. But you can generalize this such that you can place the phase on any of these phases which are fused together, and you can also allow sort of other phases to be sort of jumped around and pulled around. So for instance, if we had 3 phases here, this would be equivalent to a diagram where we place the total sum of the phase. This is assuming that there hasn't been a phase multiplier of M applied anywhere. It could be the total sum of the phase, or this is also equivalent to including pi over 2 phase on one of the gadget and one of the vertices, and then slightly updating the other vertices. And you can choose which vertices you have in this way, and these are all equivalent diagrams. And so by delaying, if you apply phase teleportation first and sort of keep track of which phases are fused together and how they can sort of interact, you can sort of allow phases to jump around. And this means that you could, for instance, apply local complementation on a vertex, which you may not have been able to before, or apply pivoting on vertices you may not be able to before, and sort of use this to allow phases to jump around. In fact, applying this tends to actually decrease the performance of the algorithm, which I'll show in a second. But and applying the phases just instantly tends to produce the best performance. And actually, in fact, applying the phases on where the phase variables on the vertices which remained at the end after applying full reduce tends to produce the best performance. I'm not entirely sure why this is, but choosing which phase you place the vertices on makes quite a big difference, even if you don't allow sort of like jumping throughout simplification or allow different vertices. Choosing which phase you put the vertex on makes a large difference. And I'm not entirely sure the reason for this, but potentially something to do with how the sort of algorithm progresses, and it selects phases which are more sort of clustered together outside, allowing better transformations in a bigger region of the graph. But it's something to be explored. So in the algorithm, in fact, we just set one of the phases to the total phase and set the others to 0, exactly as phase teleportation is done normally and normally introduced. But this could have other applications, and maybe there are specific cases where using this to allow phases to sort of jump around could be extremely beneficial. Okay, so now I'm going to move on to talking about causal flow. So causal flow is a stricter condition than G flow, which is sufficient but not necessary for a deterministic measurement-based quantum computing graph state. So for this is defined using these 3 relations. And essentially what this means is, the sort of understanding of this is that for a ZX diagram like this, the causal flow defines a set of unique vertex disjoint die-paths from the inputs to the outputs, and these essentially can be viewed as your qubit lines. One way to sort of think about what the flow conditions are allowing is to look at what's called the influencing digraph, where we draw an arrow, an arc from every vertex to its successor of the successor function, and also to all of its neighbours. And then the conditions for G flow or C flow, for causal flow even, essentially mean that there will be no cycles within this graph. This is you can view this as sort of how the information sort of temporally flows through this graph in a sort of circuit equivalent way, essentially meaning there are no causal loops. What this means is you can also, these input-output die-paths, which the flow represents, can be, so these 2 diagrams are the same just by moving spiders around on the page. These input-output die-paths essentially are the qubit lines of the equivalent circuit to your diagram. So a diagram with causal flow has a direct comparison with a direct analogy with circuits. It's almost like a more general form of a circuit where you can represent where the qubit lines are well defined at all points, and you can see the connectivity between qubit lines. And this is one of the advantages of having a diagram with causal flow, is that the qubit lines are always visible and connectivity is always visible within the diagram. Now, any diagram with causal flow can be extracted. There's meant to be a diagram here, but essentially, let me see if I can. Essentially, the way that you pull out a diagram with causal flow, if I go back, I'll just explain it from here, is that you sort of start a frontier from the outputs and you move it through, and every Hadamard edge, you then pull out into a Hadamard gate, every directed Hadamard edge, and then every phase spider you pull out into a phase gate, and then every undirected edge between sort of the qubit lines will then be pulled out into a CZ gate. So this diagram would be pulled out into this sort of this structure, where the number of undirected edges is the number of 2-qubit gates that get pulled out. And what this means is that you can directly calculate from your graph like ZX diagram how many 2-qubit gates your extracted circuit will have, just by defining the number, just by looking at the number of edges, the number of vertices, and the number of inputs. So the number of directed edges in our diagram is going to be the number of vertices minus the number of inputs, as every non-output vertex has one successor function, so has one directed edge, and then every other edge will be a undirected edge and can be pulled out into a CZ gate. So this means that we can directly calculate the number of 2-qubit gates from the diagram without having to think about how the extraction algorithm, so if it has G flow, this is not directly possible, it's difficult. as the algorithm is more complex and requires more, you can't directly work it out. So to give you sort of direct visibility of the circuit purely from the graph-like ZX diagram. Causal flow can also be slightly extended to include phase gadgets in an analogous way to how G flow is extended to include measurement planes, all measurement planes, and measurement-based quantum computing. In this, I've slightly modified how the different measurements on this. So these are looking at different measurement planes in a measurement-based quantum computing, but all normal vertices in a graph-like ZX diagram will be labeled with XY as in the XY measurement plane, and then phase gadgets are measured in the YZ, and then a phase this structure here is measured in the XZ plane. And we can't have this. We can't define a causal flow for something with this structure. Essentially, what this means is that phase gadgets, we allow a self loop. So the successor function of a phase gadget is a self, and then the conditions for causal flow essentially mean that the legs of a phase gadget are connected to a different qubit line, and that they don't create any sort of loops and cycles in the digraph. And the way this sort of works means that as you extract the circuit, the phase gadgets can be extracted using phase polynomial synthesis always, and they always are pulled out at the same point, such that you can extract them as phase polynomial synthesis. Again, using this in the for two-qubit gate reduction is difficult, and it's very difficult to predict how this will work as phase gadgets combine. Putting something into a phase gadget, it's difficult to predict immediately how that's going to affect the final circuit, as adding more phase gadgets will then allow it to sort of simplify down, and you don't have visibility on how that's going to happen in your future simplifications. So in the algorithm which I present, we don't allow extraction to phase gadgets, but it is possible to define causal flow in such a way and extract it in this way. So now moving on to the actual optimization strategy. So firstly, we translate the diagram into a graph-like ZX diagram, such that we can apply these simplification rules. We then immediately apply phase teleportation. Phase teleportation reduces the T count to such a way, and then we immediately place all the vertices, all the non-Clifford faces on the diagram, and place all the other ones to 0, and don't allow jumping, as it tends to worsen the performance of the algorithm. So now our T count has been reduced. Now we want to reduce the two-qubit gate count is now our priority. So we now list all possible transformations which we can use, and then we assign each transformation a potential for how effective this is going to be in reducing the two-qubit gate count, or whatever your goal is to reduce in the circuit. You then implement a decision strategy to choose a transformation from each one with a potential. After each application of a transformation, then you can update your list, and then once you've progressively gone through like this, then you extract a circuit. So you're essentially, rather than just iteratively applying all transformations, you're listing them all and selecting the most optimal ones each time, and then updating the list each time in the neighbours of where that single transformation has changed the graph. So the decision strategy for this, which we implement, is that we define our potential as just the reduction in the number of two-qubit gate counts. So for each transformation, the change in the number of vertices minus the change in the number of edges would simply be how many two-qubit gates that transformation has removed in the circuit. So for each transformation, we can immediately view the effect of it on the circuit and use this to select the most optimal transformations. We also require that our algorithm is going to be terminating. So the sort of full reduce simplification strategy always removes vertices, whereas here we're not necessarily always, we don't require that vertices are always removed, as reducing edges is often more optimal. So instead we require that they're not changing the two-qubit gates, so either the transformation reduces the number of two-qubit gates, or if it maintains the number of two-qubit gates, then it reduces the number of vertices, as reducing the number of vertices would just simply reduce the number of Hadamard gates. This then results in a terminating algorithm if we only apply these transformations. And in this, we always apply the transformation which reduces the number of two-qubit gates the most. One issue is that with neighbour unfusion is not guaranteed to preserve either G flow or C flow, or causal flow. So especially with G flow, applying neighbour unfusion means that you can't iteratively apply this. So in the full reduce algorithm, all the transformations are guaranteed to preserve G flow, and the specific cases of pulling interface gadgets or extracting onto boundary vertices are also guaranteed to preserve G flow. But these are not guaranteed. The other cases of neighbour unfusion are not guaranteed to preserve G flow, and there's work currently going on to provide a set of conditions for this, but we don't currently have this. And the same goes for causal flow, in that many transformations don't preserve causal flow. Many do as well, but many don't. With neighbour unfusion, we can select by choosing the set of vertices which we unfuse from a vertex. So here, in this case, we look at local complementation, but pivoting is an equivalent process. You can choose the number of vertices which you unfuse, and this allows you to essentially isolate a highly connected subset of vertices of a vertex. So you can firstly local complement on any vertex, and then also by isolating a highly connected subset, it would mean that it could provide beneficial transformations in reducing the number of two-qubit gates, as you would be able to remove more edges this way. The issue with this is that there is an exponentially large number of subsets of vertices to choose from, and you can't check all. And this problem of choosing the subset of vertices reduces to the max cut problem. If you represent the graph with edge weights of -1 if two neighbours connect and +1 if not, then it reduces the max cut problem, meaning that the choice of selecting the number of vertices, the subset of vertices is NP complete, and checking all would mean that the algorithm now has an exponential time complexity, which is something which we of course want to avoid. Instead, we define a maximum subset size to unfuse, and then check all possibilities of subsets of this size or less. And increasing this subset size will improve the performance of the algorithm, but also massively increase the time that the algorithm takes. So there's a way-off between performance and the number of subsets you choose. In the implementation which I show, we simply check all subsets, but there may be certain ways which you can immediately rule out certain ones and improve the time complexity of the algorithm by ruling out certain conditions immediately. So
sorry, can I ask a question about this?
Yeah, of course.
So of course, your algorithm, you require that you need to preserve causal flow at every step.
Yeah.
Does this always preserve causal flow?
Sometimes. Occasion. So it's, yeah, I'm going to come on to sort of how we look at preserving causal flow, but yeah, okay, yeah, sometimes these do preserve causal flow. Of course, neighbour unfusion on its own can only preserve causal flow if the input of the if the output of the sort of the vertex you're unfusing is then within so the input and the output is within the subset that you've chosen, and the subset that and those neighbours that you haven't chosen. So sort of flow would go through this central vertex that you've unfused. But there's possibility that flow can change in different ways, essentially. So it's not just a neighbour unfusion itself. You can easily check if it will preserve causal flow in that way. But it's not necessarily once you've applied local complementation on it, that doesn't necessarily hold. And it may be that this central diagram does not preserve causal flow, but afterwards it may do. And I don't have a set of conditions to describe whether these do or not. But I'll come on to that in a little bit. Yeah.
Oh,
so these, yeah.
May you go back? I wonder, is there just a unique way to choose different subset, or as long as you satisfy this bound, you can choose the subset however you want? And does that affect the optimized gate count that you ultimately get?
Yeah, so choosing different subsets will, because having different subsets that you're performing local computation on will have different connections of neighbours, and you could specifically choose the subset optimally, say using an approximate algorithm, such as in the max cut problem. There are many approximate algorithms to choose sort of the subset with the least connected set of neighbours, such that when you perform local complementation, that you're removing the most edges as you possibly can without creating extra edges in the sort of unconnected subset of vertices. But then some of these will not preserve causal flow and some will. So you have to sort of also be able to check that. So in sort of my implementation, the way that I've done it and the way that I found it is best and most general is just to check every single subset. And when I list all the matches, I check on each vertex. I'll check every single subset below a certain minimum bound, such that it's an exponential time algorithm if you allow all of these. But if S max is small relative to the size of the number of neighbours, then it becomes a polynomial. It becomes approximately polynomial. And there may be more efficient ways to check these subsets, but in just looking at how general these are. So these heat maps show the time. This is the left one shows the optimization time as a function of how large you allow this subset to be for local complementation and for pivoting. So on pivoting, we have to also include all unfusion sets on both vertices. So you can infuse both vertices, sets of neighbours from both vertices, which is why pivoting, increasing the number of subsets, increases the time significantly more than for local complementation, as you're checking subsets for both vertices. But you can see that increasing the number of subsets past 2, especially on pivoting, hugely increases the performance of the algorithm on the right here. And so you can depending on what your use case was, you essentially need to find a compromise between how efficient you want your algorithm to be. But choosing, for example, allowing two unfusions on 2 neighbours to be unfused significantly improves compared to just allowing one previously, and allowing more slightly improves the algorithm, but massively increases the optimization time as you're checking many more subsets of neighbours.
Calum, how big of circuits are these?
These circuits are run on randomly generated circuits of depth, I think, of 1,000 gates.
How many qubits?
But I have some other timing for the full algorithm, which I'll show once I've finish this. So in order to extract a circuit, we need to now preserve flow. So in preserving flow, while preserving G flow is sort of simple for everything except for neighbour unfusion. So we don't have a set of conditions preserving flow and neighbour unfusion. If we want to preserve causal flow, we can look at preserving causal flow locally. So you can define a subgraph of within your transformation subgraph, where, so say in this box is where the transformation has changed the number of vertices. So we define any vertex which has had its neighbour set changed to be within this transformation subgraph. And as the flow is unique, essentially, but we're looking at locally flow preserving transformations here. So the flow external to this, we would be assuming to be the same successor function. And then by defining our inputs and outputs, where the flow externally sort of enter this transformation subgraph and exit, this must also have a flow with the same success function, be able to fit into the flow of it externally. So you can define the transformation subgraph like this. And the first condition for local flow preserving is that this transformation subgraph also preserves flow in just the number of vertices, in just the flow of vertices. But you also need to check that this flow is then connected to the previous flow and will not create any cycles in the influencing digraph. So you may have a flow where the flow lines still connect together, but if it creates a cycle in the influencing digraph by changing the number of neighbours, so in this diagram I haven't drawn any connections between any undirected edges between connections, but there may be a certain number. You then need to look at the what we call the first influencing digraph. So where I1 includes all neighbours of vertices inside the transformation subgraph. So inside this influencing digraph is where the flow can change. So if you look at the influencing digraph, the flow can change as the flow sort of affects the neighbours of the vertex that it goes to, as well as this. So you also need to check that this also preserves flow, and that there have been no cycles created within this within these two things by changing the transformation subgraph. You can do this. The best way to do this is to simply just recalculate the flow. So there's an efficient algorithm to calculate flow, and the simplest way to do this is to firstly check the transformation subgraph preserves flow, and then calculate this for the influencing digraph as well. And that ensures that there are no cycles within this influencing digraph. You then also need to check the other condition, which you need to check is that there have been no cycles created within this influencing digraph and outside this influencing digraph. So even though the flow may not have changed outside this influencing digraph, you may have created a cycle which goes inside this and then comes out just from the nature of how the neighbours have changed and how the flow has changed. So the way that you can check this is to look at each pair of vertices within this influencing digraph. So within the neighbours of where the transformation has changed the graph explicitly, and compare the partial order of these and ensure that if the partial order induced by the flow outside of the influencing digraph does not then contradict the partial order of the flow created inside the influencing digraph. And by checking all these relations, then that guarantees that your flow will be preserved. However, I know that in order to check these relations between these two vertices, U and V, and all vertices within this influencing digraph, you need to use a algorithm to find the flow which has a slightly higher time complexity than just an algorithm which finds the flow efficiently, as it also needs to fully calculate the partial order. So this but checking these will ensure that your flow is preserved. However, this is sufficient, but this is not a necessary case for flow to be preserved. So, for instance, your flow may change whilst in this area of the graph, the actual graph is not changing. The flow can change in such a way exterior to this, such that flow is preserved overall, but flow within these will not be preserved. So in this case, we don't have the same number of inputs and the same number of outputs coming into the influencing digraph. So when you just define these as the sort of inputs of the original flow, you'll find that there won't be a flow, but flow can be preserved by sort of externally changing the flow. And this can be, so global changes can happen at any point. It is much more likely that the flow changes within the sort of influencing digraph, and you could define sort of wider influencing digraphs and wider transformations and sort of do this where you do the same procedure, but just take the next set of neighbours outside, and each increasing the size of these will increase the probability that this preserves flow. So if you had a huge graph, and then this would allow you to sort of check flow. But the most like sort of general way, and the way that I found was actually fastest for the size of circuits, which was benchmarking on up to several thousand gates, is to simply just recalculate the flow of the entire graph each time. So here, these are the different algorithms that you can use to find flow. So on the left here, is the G-flow algorithm, which you can see is significantly, it scales very badly with the number of vertices in the graph, which means that for checking neighbour unfusion with G-flow, it's not really feasible to do it in the same way, where you check all vertices in this way. But with causal flow, the algorithm, so that the red algorithm on the right is the algorithm which simply calculates the flow and tells you if there's a flow or not, and it will produce a successor function, but it doesn't calculate the entire preorder and give you a function which allows you to compare any two vertices and define the partial order between them. Whereas that's what this orange algorithm does. So if you were to be locally preserving flow, you would need to use this orange algorithm such that you can compare the sort of relations and ensure that no cycles have been created between the external. So for my algorithm, after each transformation, I simply just recalculate the flow of the entire graph using this red algorithm, as it's a very efficient algorithm. It's linear time, and for the size of benchmarking graphs that I'm looking at, it's more optimal. It's more optimal, more general, whereas checking locally would sort of be approximate, as it doesn't allow checking for sort of global changes in the flow. So after every single transformation, before each transformation, I just simply apply the transformation and then recalculate the flow of the entire graph. And if it preserves flow, then I allow that transformation to occur. Otherwise, I reject it. But maybe if you were to get huge graphs of hundreds of thousands of gates, then there would become a point where a compromise of just checking flow locally is it's likely that flow will become more efficient and become more optimal, or approximately optimal. So there's a sort of compromise there. Okay, so looking at the results of this algorithm now, these are the results on randomly generated circuits. So you can see that. So first, I compared to the previous sort of best ZX calculus space method, which is the green and red graphs here, which use a potential, which is just reducing the number of edges, and they allow. And the key here is where G is preserving G flow and C is preserving causal flow, and then the superscript index is the number of unfusions, number of fusions that I'm allowing on each vertex. So you can see that increasing the number of infusions allows better reduction in two-qubit gate counts, and still for just simply applying the full reduce algorithm is optimal for when there are low probability of T gates, but as soon as it becomes higher, this can produce higher, and whereas this algorithm sort of generally produces an even reduction in two-qubit gates across, independent of the number of T gates. For total gate count, it sort of tails off as optimizing, as it's not trying to optimize the number of Hadamard gates. So it essentially tails off as optimizing this. And then you can see the time in the number of gates. And the reason that the previous algorithm for G-flow here takes so much longer is that at a point it has to recalculate the G-flow because of neighbour unfusion. So it's using neighbour unfusion, and that's why the time complexity just becomes huge. So increasing the number of unfusions which you allow increases the time, but it also increases the performance. So again, there's a way off. And then looking at sort of the benchmark circuits.
Calum,
yes.
can you go back to the previous slide?
Yeah.
So I'm a little bit surprised that full reduce would do better than your algorithm. I would have expected that, say, if you give it a full Clifford circuit, that your algorithm would still be able to compete, but it looks like whereas full reduce goes to normal form, yours doesn't. So does the fact that you restrict to things that only have causal flow allow you, does that mean there exist Clifford circuits which cannot be reduced to normal form without breaking the causal flow structure?
Yeah. It's essentially like the normal form, especially as I'm not allowing phase gadgets to be extracted. It can't reduce itself to that normal form. And I think it's also partly the extraction algorithm, which once it's in a normal form, the sort of Gaussian elimination actually does quite a significant amount in that case. It doesn't from graphs with causal flow, applying the sort of normal extraction, sort of Gaussian elimination extraction generally doesn't change the results, except in one case, which I'll show in a second. But yeah, I think it's allowed because I only allow transformations which reduce the number of this heuristic I've defined as the number of two-qubit gate counts. By maybe allowing them to sort of increase once and then allowing it to reduce before can sort of lead to better transformations, and maybe in the future you could use some sort of annealing algorithm to decide whether maybe increasing some may be more beneficial. But yeah, so it doesn't for purely Clifford circuits, the full reduced algorithm is still sort of much better at producing the number of two-qubit gates. But I think that's just because I'm restricting the number of potential algorithms, number of transformations that I'm doing, such that they always reduce the number of two-qubit gates, and that leads to this sort of better performance when there are a lot of non-Clifford gates, but it won't necessarily be as optimal. So it may be that preserving G-flow is optimal, but it's actually this neighbour unfusion which allows you to which provides a significant amount of optimization, and we don't have if we had a sort of algorithm for G-flow, or a way to know whether neighbour unfusion in this way would preserve G-flow. So I think there's been work looking into single vertex neighbour unfusion, looking at things like Pauli flow and how this is preserved. But for G-flow, like for a general number of neighbours to be unfused, if you had some set of conditions, it may be able to produce better optimizations just preserving G-flow, not causal flow. But then also the advantage of causal flow is that you always have visibility of your circuit. So if you wanted to preserve sort of if you were working in an architecture based and you always have visibility over the connection between the qubits. So if you could use this in a way to optimize different routing techniques and things, and also so transformations with like circuit-based like equivalencies could be translated directly into ZX-based things. So any sort of circuit rule, it's a gate cancellation or anything. If you translated that in and defined where you need qubit lines, these could be extra rules which could be applied on graphs of causal flow as you know where your defined qubit lines are, essentially. So that's all the benefit, but it may be that preserving G-flow still produces better optimizations. So these are on the sort of standard benchmarking circuits, and you can see that the average, increasing the number of unfusions means that we get a very, very high reduction in two-qubit count, which betters the sort of this NRCM algorithm, which uses many sort of circuit gate cancellations, and on many of the circuits it finds new bests, but improving past allowing 2 unfusions only improves slightly, whereas the time increases quite significantly. So there's sort of a balance there, but it improves significantly compared to 1. And on many of these circuits, it finds optimizations which were not found before, like so for instance these GF mulk circuits, often they were just not improved at all before, whereas this finds quite significant reductions for several of them. Yeah, and it produces overall better optimization performance relative. The last thing that I want to note is that, like sort of an observation, is that, which isn't directly related to this, is that the performance on quantum Fourier transform circuits, on the benchmark quantum Fourier transform circuits, is that if you applying the C-flow algorithm does not reduce the number of 2-qubit gates at all, and the same with NRCM. But if you applying the G-flow algorithm and this quantum Fourier, this QFT algorithm, which I was saying in a sec, reduces the number of 2-qubit gates to exactly the number of T gates. And in all the ones that I checked, it reduces this. So I don't know. I haven't explored whether this is, like, I haven't explored this analytically yet. I haven't seen this noted in anything else. But this is essentially a cause of the extraction algorithm alone. So if you apply the same transformations and it has C-flow, causal flow, and apply it, it won't reduce it. But if you apply the extraction algorithm, the way that the sort of Gaussian elimination works means that. So, for example, this is a QFT 8 circuit, quantum Fourier transform 8 circuit. Simply by applying phase teleportation and then only applying identity fusion, so removing identity vertices, fusing vertices together, and then using the G-flow extraction. That's all that's required to get to this form where the number of 2-qubit gates is exactly equal to the number of T gates, and it appears to be it appears to find some normal form. I haven't seen any paper which references this before. This isn't the nature of the sort of causal flow algorithm, but it's something which is of note, and in particular sort of links the Gaussian elimination, which does it on the reduction of the structure of quantum Fourier transform circuits. It appears to find some sort of normal form. But yeah, that's all then. So I think I slightly overran, but has anyone got any questions?
So just checking this, like, did you run some verification tests to make sure that the circuits optimized are semantically equal to the originals and stuff? But like, you're pretty confident that the algorithm implements correctly? Yeah. Every circuit was tested, was confirmed to be equivalent to the previous circuit. Yeah.
I have a question. So just now you mentioned that because you're checking every vertex, so the scalability would be an issue. I wonder, would it be possible in order to improve the scalability, to slice the circuit into sub-circuits, and then you have like maybe multiple computers that you could check every slice independently with each other. If this is like not possible, what would be the issue? Or if this is possible?
Yeah, this would be possible. You could do this. It would be slightly like, it would be approximate in the same way that checking flow locally would be approximate, in that transformations between these could happen where flow changes between these sort of subsets that you've defined, or transformations sort of where that allow flow, that maybe a flow can be like, could change in one subset of this circuit, and then or the transformation which you apply in one subset of the circuit won't preserve flow in this subset, but may preserve flow locally if it globally changes outside. But I think doing that would be a feasible way to get an approximate algorithm. And I think almost all transformations locally preserve flow, at least in some local region, as it's unlikely for there to be sort of transformations which change the flow outside, because often these will create cycles in the influencing digraph. But that would be a way to sort of, especially as if you wanted to improve scalability, to sort of get find an approximate solution to this algorithm, which would also produce probably, I imagine, extremely similar performance. So yes, for much bigger circuits.
Thank you.
Leah, you want to go ahead?
Hello, sorry, I couldn't find my mouse. Thank you for the talk. My question is, has these causal flow preserving rewrites, has it been connected to any known rewrites for tensor networks, or combined? Have you combined the empirical results with as a pre-processing stage before tensor network contraction or optimization?
No, I haven't, but it's something which is definitely like something which could be done, and it's not something which I've explored. I haven't explored it myself, but it's definitely something I've thought about when applying these along with other, often with previous like ZX calculus based optimizations, applying them prior as a pre-processing stage and then applying other ones can be extremely beneficial. So yeah, it's definitely a method to explore. It's definitely something to explore, but not something that I've explored myself.
Yeah, thank you. That'd be really interesting to know.
If I can maybe add to that, there's this work by Johnny Gray on tensor network contraction, and he considers hyperindices. And if you translate this to ZX diagrams, then a hyperindex is just a Z fiber without a phase. And so when you're doing sort of this spider infusion, this is kind of like splitting a hyperindex into two components, and that is something he considers, and he tries to find sort of optimal ways to do this. So like I think there is something of a direct translation there, although of course he doesn't care about flow. He cares about like what is like what condenses the graph in such a way you can more easily contract.
Yeah. Okay. Yeah, and I think also in terms of just using circuit like the normal like circuit-based optimization methods can, as you have visibility of the qubits, they can also be implemented into this algorithm rather than sort of applied as a separate algorithm. I suspect I haven't explored it too much myself, but there'll be ways to, as you have visibility over the qubit lines and how the connectivity works, sort of you may be able to define particular translation rules, which are simplifications which are conditional on flow. So have a flow going this way, and have different rules which condition on how this flow works in a similar way to sort of circuit-based rewrite rules.
Sarah, go ahead.
Oh, thank you. So I wonder, when you do the transformation, do you think you could use some of the restrictions to derive sorts of like lower bound for the gate count given a circuit? Meaning that because of like the flow preserving restrictions, you can do like the best you can do would be reducing, for example, like T gates up to certain numbers, or reducing the 2-qubit gates to certain numbers.
I'm not sure. Potentially, I mean, the thing is with like even the T gate count. So these reduce the T gate count in the same way that phase teleportation does, which matches several other algorithms. But if, for instance, it was showing that combining this sort of T gate reduction with the Todd algorithm reduces the T T count even further. So I'm not sure how you would implement that, like sort of combine that together. Although that algorithm massively increases the 2-qubit gate count and doesn't really work for optimizing both. But potentially yes. And I also think there are ways which you can prune like transformations faster than I do, and I've sort of applied it generally where I just check blocks. But I think there would be ways where you can prune certain transformations and immediately rule them out as they like, rather than define like a set of conditions where flow won't be preserved in this way, and you can immediately rule these sort of things out. And as there is like a condition for a minimum, I can't remember exactly what the relation is, but there's a relation for the number between the number of edges and the number of vertices and things where if there's where given that relation, you can immediately rule out that there will be a causal flow. Like there's a limit on if there are essentially too many edges. But potentially. Yeah.
Sorry, I wonder, could you tweak your algorithm such that you could potentially work with NISC architecture so that you could account for the nearest neighbor interactions between the 2-qubit operations? Since you're already doing lots of restriction check, I just wonder, maybe just adding like encoding such restrictions is just one more step, and you already have the nice mechanism to check it.
Yeah, for sure. And that's like one of the benefits of preserving causal flow rather than G flow, is that then you can do things like that where you have visibility over the connections, and there's definitely something which could be assured. Although I'm not sure how you would you could change the connection one, but then another one can remove it, sort of. So I don't know how you would want to sort of like restricting it to always maintaining different connections would restrict quite a lot of different transformations. But I think there's definitely ways that could be explored to sort of utilize this within that, for that purpose, as you always have visibility over how your circuit is connected, essentially.
Thank you.
All right, so are there any more questions from Calum?
Yeah, I wanted to ask if this excellent work, by the way. I just want to say if you have your master thesis uploaded somewhere, or you want to publish, or you plan to publish a paper on this, because I would love to read in more detail.
Yeah. I'm just finishing up a paper essentially now. So yeah, it will be. I think it'll be hopefully sort of soon. Hopefully, sort of releasing a paper where it specifies more of these sort of conditions in a more formal way.
Okay, thank you.
May I ask, just now in the optimization strategy, you said you're assigning each transformation a potential. What is that potential about? As in,
so in this case, the potential is just I'm defining the potential as just the number of two-qubit gates it reduces, and that's just that. But you could, in theory, so the previous algorithm just defines it as the number of edges that's reduced in ZX calculus, but you could also weight So I haven't done it in the most recent stage of the algorithm, but you can, by weighting different transformations, different amounts, you can assign sort of a different potential to each based on that. So maybe for instance, it's beneficial to assign more weight to a pivot rather than a local complementation, or maybe delay applying sort of the identity fusions. And you could potentially use sort of machine learning to try and optimize these parameters of how you weigh, and use different sort of, as well as how many two-qubit gates it reduces, so define a better potential, which allows you to then sort of increase it. But here the potential I've just defined is just reducing the number of two-qubit gates.
So basically you give them like a way to, like, basically this gives you a way to decide which transformation that you pick among many candidate transformations.
Yeah, you're essentially just like
whichever.
Yeah, you're essentially just like ranking all the transformations in order of how like beneficial they'll be in reducing the extracted, in optimizing the extracted circuit. So in this case, I just like the most simple way is just applying the one that reduces the two-qubit gate count for most. But then, in order, for instance, like to decide between two that reduce the two-qubit gate count the most, and maybe optimal to apply different ones that maybe one of them removes more vertices or removes less vertices, or applying different transformations and weighting them in different ways could you could do more advanced machine learning algorithms based on how this connectivity works or something. But essentially, yeah, you're just like ranking the effect of each transformation.
Thank you.
Okay, if there are no more questions, then I suggest we thank Calum again in whatever way Zoom allows you to do, like typing or emotes. Thank you very much, Calum, and good luck with